In this video, I'm going to go over the steps of conducting a repeated measures t-test. As I've mentioned before, I think that this is easier than an independent samples t-test. Instead of looking at two different samples, we're going to be looking at a set of difference scores. So let's take a look. Here's the research scenario. A forensic psychologist is interested in knowing whether women wearing glasses are rated more favorably than women without glasses to determine whether this may influence jury opinion. So there were 9 study participants in this mythical study. They were shown a set of 30 photographs. 15 women were shown twice in the set of 30, and each woman was shown once with glasses and once without glasses. So we're going to use a 0.01 level of significance test, two-tailed, to determine whether the photograph with glasses was rated significantly different than the photograph without glasses. So we are going to follow the same 4 steps of hypothesis testing that we've been doing all along. We're going to start by stating our hypotheses. We're going to set a critical boundary, which we actually already had, alpha 0.01 for a two-tailed test. We're going to locate where our critical region will be for this two-tailed test. We're going to calculate our t-statistic, and we'll make a decision. First, we need to state our null and our alternative hypotheses. So we have the null hypothesis is that there is going to be no difference between the photographs. And what you see here is the population mean and a D. That means the mean of the difference scores. And we're saying that the mean of the difference scores is equal to 0. In other words, there's going to be no difference between the two photographs. The alternative hypothesis is that there will be a difference, that the difference scores will not equal to 0. So we're going to locate a critical boundary for this problem at alpha 0.01, and we'll locate it in the t-distribution. So we have 9 participants, so that means our degrees of freedom are 9 minus 1, so we circle 8. And we have 0.01 in 2 tails combined, which means 1% combined in 2 tails, so we have a 0.5% in each tail. And our critical t-value is 3.355. So 3.355 is going to be our critical boundary. The first thing that we're going to need to do is to calculate the difference score. And I have the set of data here, but I'm actually going to show this to you on Excel. I've also included this Excel sheet right above this video. So if you would like to download the Excel sheet and follow along, you might want to do that, or you can download it for later and give it a try yourself. Let's take a look at the Excel sheet. Here is the Excel sheet where I have everything set up for you already. So we have our participant numbers here, ID numbers. Those aren't numeric, that's just categorizing each participant with a number. And then we have the favorability ratings that the participants gave for individuals without glasses and for individuals with glasses. And the very first thing I need to do in a repeated measures t-test is to find the difference score between with glasses and without glasses. And so what I'm going to do, because order matters in my interpretation, I'm going to take the second group and subtract the first group. And if the second group has higher ratings than the first group, that means my difference score will be positive. And I can interpret that to mean glasses are rated more favorably. I could certainly do the t-test in the other direction, but for interpretation purposes, it's easier for me this way. So what I'm going to do is I'm going to find my difference scores first, and I'm going to do that by taking the with glasses score minus the without glasses score and hit return. And I'll do that for all of these. Now that I have my difference scores, this is actually the data that I'm working with. I'm going to ignore the rest of that. The difference scores are what I'm looking at. I want to know if my difference scores are significantly different from 0. If somebody didn't have a preference between with or without glasses, their difference score would be 0. I want to know if these difference scores are significantly different than 0. To do that, I need to do a t-test, which is going to require the difference, the mean of the difference scores divided by the standard error. Well, to get the standard error, I need the variance. To get the variance, I need the sums of squares. And then the sums of squares is where we're going to start. But to be able to do sums of squares, I first need the mean. So let's find the mean of all of these different scores. I can sum up these scores first. So I'm going to hit equal. I'm going to press in sum, double click it, and I'm going to select all of these scores to add up. And then to find the average of these different scores, like we've done before many times, equals, I'm going to select my total and divide it by my n of 9. So the mean for this group of different scores is 3. Now that I have the mean of the different scores, I can figure out this sums of squares. Now your sums of squares formula is the sum of each score minus the mean squared and added up. Well, just substitute that letter D right here for the score. D is our score. So here we go. Let's take our first score and subtract the mean of 3. And I'm going to do that for all of the rest of the scores. Now as a reminder, I'm going to go ahead and come down here and I'm going to check to see if all of my deviation scores equals 0. And they do. So I'm good. I'm in good shape. I did it right. All right, the next thing we're going to do is we're going to square these deviation scores. Remember, we take each score minus the mean, then we need to square it. So let's do that. I'm going to take each score. I'm going to do the little caret and a 2 for squaring. And I'm going to draw down. All right. Now, what you're asked to do is to sum, the sigma means sum. I'm going to sum all these deviation scores to get my sum of squares. Another way of saying it is sum of squared deviations from the mean. So double click on that. I'm going to sum all these up, add them up for 18. So I know my sums of squares is 18. So I can do everything now. Now that I know sums of squares, I'm free to do the rest. First of all, let me put in my n is 9. So my degrees of freedom are going to be equal to 9 minus 1. N minus 1 is your degrees of freedom. I already put the critical T in there for us. So now we need to know our variance, because variance is part of this standard error calculation. If you will recall, variance is simply the sums of squares divided by n minus 1. The reason why we have n minus 1 in the denominator is because we're working with a sample. We don't have access to the full population. We need to make this little adjustment right here because our samples have less variance than the population. So we can find the variance of this sample, which is estimated what it would look like in the population. So here we go. I'm going to go equals. I'm going to pick my sums of squares, which is this right here. I'm going to divide it by n minus 1, which is my degrees of freedom here. So my variance is 2.25. Now the final part for the denominator of the T formula, this standard error of the difference scores, is going to be the square root of variance divided by n. So we can do that, right? So I'm going to come over here, I'm going to do an equals, I'm going to put square root. And it's saying, well, what do you want to do the square root of? And I'm going to do the square root of my variance divided by my n of 9. Remember, we already made the adjustment in the variance itself, so we don't need to do degrees of freedom. We're using 9 here. That means my standard error is 0.50. That means that I could expect different scores to be different by about 0.50 of a unit, just due to random error. That's normal, that's what's expected. What we're going to find out is, are our different scores significantly more than what is normal or expected? It's a ratio. So what we're going to do is we're going to look at the T formula here, and the numerator says take the mean of those different scores minus the mean of the different scores in the population. Now, The mean of the different scores in the population, the estimate, the null hypothesis is 0. So this second part is always going to be 0, and in fact, you can just ignore it altogether because anything minus 0 is that one thing. So we have the mean of our differences divided by our standard error. That's all we need to do now. So I'm going to do that. Equals the mean of our differences, which was 3, divided by our standard error of those differences, and we end up with a t of 6. So we have to decide now what we're going to do with that t of 6. This is a two-tailed test, and our t is positive, so we're going to evaluate that against the positive value of our critical t, which was 3.355. We found that on the t-table. Is 6 more extreme than 3.355? Absolutely it is. It is further out in the tail. And when this happens, we can reject the null hypothesis. We're rejecting the idea that there's no difference between these two groups. There is a difference between these two conditions without glasses and with glasses. And so we reject the null hypothesis. We find a statistically significant result. Let's take a look and see what that would look like written up. So we could present the statistics that we found. We can say that the p is less than 0.01 because our t was in that critical region. We had set our alpha at 0.01 and our t was within that critical region, so we can say our p-value is less than 0.01. The probability of finding our t statistic if the null hypothesis is true is 0.01. In other words, it's very rare. And since our finding is so rare, we reject the null hypothesis, and we conclude that there was a statistically significant difference between the photograph with glasses and the photograph without glasses. And because we know the direction that we did the subtraction in, we also know that glasses are rated more favorably because we had a positive number and because we subtracted without glasses from the glasses score. Anyway, that is our t-test for repeated measures. Pretty easy, I think. In the next video, I'm going to talk with you about advantages and disadvantages of a repeated measures t-test. I'll see you there.